Hi, my name is Daria, and this is my final project for CSIE-63 Big Data Analytics. It's entitled Big Data Case Study, Institutional Research, and Neo4j. I'm going to give you a quick overview on what I'm going to cover in this presentation. So we'll first introduce the project itself and what my motivations are for the project. I'll talk about the goals of the project, and then finally I'll talk about the actual project itself, the data loading, the data analysis, and data visualization. If you're interested in actually taking a look at the working demo or the source code, you can find it on these two links. So the first link is the actual demo of my final project, which is hosted on shinyapps.io. And if you're also interested in the data itself, you can find it on GitHub at the link below. So quickly about myself, my name is Dari Dalal. I am a research analyst in the Office for Institutional Research. And institutional research is looking at the broad institutional research is a broad field that aims to understand how colleges and universities operate, from admissions to financial aid to faculty productivity and research impact. And they attempt to use the university data to aid in policy and decision making. So in class, we took a look at Neo4j. It looked really cool. Unfortunately, we didn't really get a chance to play with it in a more substantive manner, since our homework was really just a toy example of creating a couple of nodes, and that was the extent of it. So I was really interested in the Cypher query language, and also thinking about data in a graphic and network type way, and seeing if we could apply some of that insights to institutional research. So the main goals for this project was to see if I could actually load the citation network data into Neo4j. That is a large data set in memory. I think part of the challenge was that it was hard to figure out, what was possible within the context of the homework that we did, and so I wanted to see if it was scalable for the large data sets that we work with in our office. The second thing was to then take a look at the Cypher query language and see if we could use it to answer novel IR questions about research productivity. And then finally, we're going to just take the visualizations that we created based on the queries that we ran and create some interactive R visualizations that I was going to host on shinyapps.io using rshiny. So the overall workflow for this could be kind of summed up in 4 steps. The first one was we're going to attempt to load the data in Neo4j using an embedded Java app. Then we're going to analyze the data using Cypher, the query language for Neo4j, as well as R and RNeo4j. Finally, we'll collect and visualize the results in an rshiny app, and then we'll deploy the app on shinyapps.io. So let's talk about the data itself. The data is from Aminer, which is an online collaborative computer science citation network source. They have compiled computer science citation data from over many sources, from DBLP to ACM. They have the data set that we're working with is actually especially large. It's about 2 million papers and 4.3 million citation relationships. So compressed, it's about 137 megabytes. Uncompressed is about 257 megabytes, which is quite a bit to read in memory. The original data set itself is in block format, which you can see below. Basically, each block represents a paper, and each line is a property of that paper. So we have a title, we have the authors, we have the papers that this paper cites, as well as where it's published. And luckily, I didn't have to do work with this data set. A colleague of mine, Albert, was interested in parsing this data, and so he had actually created a JSON file that was a parsed version of this using Scala, and so that was my starting point for the project. The JSON file basically had a single JSON object per row per paper, and each paper basically had all the properties nested as JSON elements. Our eventual solution will be using Java to create the Neo4j graph and nodes, which this snippet of code shows. So the overall strategy for creating the nodes was pretty much first, we're going to create a Neo4j graph object. Then we're going to create uniqueness constraints for the paper, author, and journal labels. We'll read in the JSON file line by line and parse the JSON object. And then basically for each line, we're going to do the following. We're going to first check to see if the paper exists in the graph. If it does not exist, we're going to create the node and set the properties, i.e. the title, the journal it was published in, who the authors were, and so on. Next, we're going to loop over the authors itself, and we're going to check to see if the author exists as a node in the graph. If it doesn't, we'll create the node, and then we'll create the relationship between the paper itself and the author node that we just created. Next, we'll check to see if the paper's journal exists in the graph as a node. So again, if it doesn't exist, we'll create the node for the journal, and then we'll set up a relationship between the paper and the journal. And then finally, we'll loop over the citations, that is the papers that this paper is citing, and check to see if those papers exist as paper nodes in the graph. If it doesn't, create that node and then create the relationship. So the data model that we came up with looks something like this. The goal is basically to create a separate node for the paper, a separate node for the author, and a separate node for the journal. And then ideally have this relationship where the paper is written by an author and the author writes a paper. The paper is published in a journal, and the journal has published a paper. And then finally a paper cites another paper, or a paper is cited by a paper. And so in this data model, I'm using the Neo4j kind of syntax where the nodes are enclosed in parentheses, the relationships are enclosed in brackets, and the properties for this graph are represented in brackets as well. In curly braces. And so the data model, even though it's pretty straightforward, you could create a lot of inferential relationships. For example, if you're interested in all the authors a journal has published, you could basically go from journal to paper to author, and through following that loop, you'll be able to get all the authors that a journal perhaps has published. So, data loading. Things did not really go all that smoothly when I was trying to do this. Initially, the attempt to create a graph DB with our Neo4j was not scalable. Basically, based on the calculations, I projected that it would take about a year to load all my data via R. So that was a no-go. Second attempt was to use Java, kind of similar to what we did in class, using the Java embedded app. It was slightly better, but still untenable. I'm not really a Java guy, so probably the code I came up with was not the most efficient. But I was able to end up at least loading about 60,000 rows, which came out to about 200,000 nodes. So it took about 10 minutes to load 10,000 rows, which projected out to about 1.5 days if you want to load the full data set. It was a constant big O of n for load time, but as you can tell in this graph, it's a linear growth. So as we start approaching the 2 million nodes, the time it takes expands linearly. One of the challenges with Neo4j is that it runs on a single machine within a single memory space, so you can't really parallelize data loading. One of the things I tried to do when I was in R was to see if I could use R, some of the parallel libraries in R for loading, where basically you could create multiple R processes and split up a task. But what ended up happening was that those multiple tasks tried to create multiple connections to the Neo4j server, and they did not load anything. So that didn't work as well. And I ended up just using the embedded Java app and aborting it after 60,000 rows, which is about an hour. Again, this was probably the most frustrating part of the project. It was just not scalable, and I'm sure there's more scalable solutions, but being unfamiliar with this product and being unfamiliar with data loading in general, I wasn't able to get too far. Anyway, with the nodes I was able to load, we were able to at least create a graph. So I was able to actually load up Neo4j and get a graph that looks something like this. If you were interested in a live demo, for example, here's my Neo4j instance, and if I were to return the if I'm taking a look at just the top nodes, we could see that we have some data in here and some relationships. So apologize for that. So basically, if I just return the 100 random nodes, you can see that for all the nodes I did manage to load in, I have relationships. So for example, I have in green here my journals, and for each journal you can see the papers they've published, which are in blue, and then you can see the authors who wrote those papers in red. And as you can see, there's some really cool movement in my graph in terms of the structure, overall structure of the graph. So if we take a step back, basically I was based on my Java experiment, I was able to load in 200,000 rows, of which 82,000 approximately were author nodes, about 11,000 were paper nodes, i.e. the papers that were published, and then finally I was able to create about 500 journal nodes, which are the actual places that the papers were published. Next, I would kind of want to actually see if I could use Cypher to answer some questions. So the first question I asked was, who has published the most articles and what is their longevity score? So calculating longevity, this I got from A minor again, is basically you take the person's most recent paper and the first paper they published and basically subtract the year of the most recent paper, or sorry, the year of the first paper published from the most recent paper, which will give you how many years they've been around producing research. So here's my Cypher query. It's relatively straightforward. Basically, I matched the author node based on the relationship wrote for the papers they wrote, P, and then I returned back the name, the count of the papers, and then I did a inline calculation where I took the max year of their papers and the min year of their papers and returned that as long score. So the final result was a chart that looked something like this. For my project, I use R charts to do the visualizations. R charts is a really cool library. It's a R wrapper library that basically allows you to create interactive R visualizations relatively simply in R. So the end result is you have something like this where you have really cool interactive charts that you can hover over and zoom in, zoom out, and add and remove series. So the second question I looked at was, who are the rising stars? So rising star is someone whose first publication was in the past 5 years. Again, we used the same Cypher query in problem 1, but this time I removed the limit. I wasn't quite sure how to filter results after they were aggregated, so I ended up doing the filtering in R itself using dplyr, using this little chain here. And the dplyr chain basically filtered my query results on longevity scores that were less than 5 years. Rearranged the data frame in descending order with the most citation counts on top, and then finally selected the top 25 rows. And again, I visualized this using R charts and had a visualization that looks something like this. The third question I looked at was, which author has the most co-authors? So we call this sociability. So to calculate the sociability score, I used the following metric, where I took basically 1 and added it to the sum of all co-authors a person had across all papers they had written. Again, this is from A minor. So the Cypher query is below. It basically creates a path where it maps out all the papers written by an author and also all the other authors who co-wrote that same paper using this match statement here. And then I just counted distinct authors for each paper, and I limit it to the top 25 results, and we get a really cool looking chart that looks something like this, where Nicholas Jennings is our most sociable researcher in this data set. Finally, I was taking a look at which journals on average had the most citations per paper published. First ran the Cypher query in like so, but since I didn't know how to deal with Cypher to answer the specific question, I kind of used another dplyr chain to do some further analysis, aggregating the results by journal and then dividing the total number of citations by total number of papers to get my average citation score. And then finally I was able to visualize it. And once I had done all this analysis, I put it into an RShiny application, which consists of 2 parts, a UI.ir as well as a server.r file. So the UI just sets up how the page looks, and the Shiny app sets up, the server side sets up the actual chart rendering of the charts and uses UI bindings. And then finally, I deployed it using shinyapps.io, which is basically a single button click in RStudio. It's really cool. And once it was deployed, you had the final result, which is my working demo. That's it. That's my presentation. Thanks for